Hello and welcome to the seventh part of these talks about fundamental mathematics, this time adding two sine waves. Adding two sine waves is really quite easy provided the sine waves are at the same frequency and are in the same phase. And what I mean by in the same phase are they both start at the same point in their cycle at the origin of time. In this case, t equals 0. This one is starting going up, just like a normal sine wave would, and so is this one. So we can just add the two amplitudes. The 0 to peak amplitude in this case is A, the 0 to peak amplitude is B. The sum of these two waveforms would be another sine wave of amplitude A plus B. The problems come when we want to add two sine waves which are not in the same phase. Here I've plotted a sine wave in blue, just the one of it. I can add another sine wave to this display, like so. It's in red. You can't see the blue one anymore because it's underneath the red one. If I reduce the amplitude of the red one, you'll be able to see both of them. Now, these sine waves are in phase. They have their maximum point at the same time. They go through 0 at the same time. They have their minimum point at the same time. So adding them up is just a simple case of adding up the amplitudes of the two sine waves and producing another sine wave which has the sum of the two amplitudes. That is quite straightforward. Things start to get interesting when the sine waves have different phases. Let's go back to the same amplitude, and this time I'll change the phase of one of the waves with respect to the other. And by changing the phase, I mean adjusting when it has its maximum and when it has its minimum. So I could, for example, do something like that. The red now has its maximum point at a different time from the blue. Now, if I add this red waveform to this blue waveform now, what I get is that. It's another sine wave. This is quite a remarkable property of sine waves, and one of the reasons that we use sine waves so often in analysing circuits. If you add two sine waves of the same frequency, it doesn't matter what the amplitude and the phase of the two sine waves is, you will always get a sine wave. This is not true for almost any other waveform. For example, if I added two square waves together, the result would look like this, a kind of a strange stepped waveform. And if the amplitudes were different, I can get a variety of interesting looking sum waveforms like this. If I had let's say, a triangle waveform, if the amplitudes and the phases are the same, I would just get a larger triangle waveform as the sum. But if the phases differ, then the output sum is no longer the same shape as the inputs. In some cases, it looks a bit more like a square wave. But for sine waves, add two sine waves together, and you get an output sine wave all the time. It is a very common problem in electronics to work out what the sum of two input sine waves is. It's not a particularly easy problem, except in some special circumstances. We've seen one of the special circumstances already. If the two sine waves are in phase, we can just add up the amplitudes. There's another special case where one of the sine waves is exactly 180 degrees out of phase with the other. We say 180 degrees because if we were plotting this sine as a function of angle, then it would be 360 degrees from here all the way around to here. So this red waveform is 180 degrees, half of a whole cycle away from the blue waveform. And in this case, we can just subtract the two amplitudes. If the two amplitudes were the same, then the result would be nothing, 0, just a straight line. but in the more general case, where the amplitudes are different, the amplitude of the resultant sine wave is the difference between the amplitudes of the input sine waves. It's when the phase isn't either 0 or 180 degrees out of phase that things become a bit more challenging to calculate. The phase is closer to the phase of the larger waveform, but it's always in between the phase of the larger waveform and the smaller waveform. But how do you calculate exactly what the amplitude of this waveform is? Well, there are several ways to do it. Probably the easiest way to do it is one that you won't come across until you've learnt about complex numbers. Until then, we can do it a slightly more complicated way. Okay, let's consider the case where we've got two sine waves that we want to add up. I'll call the first of them x of t equals a sine omega t plus a phase that I'll call alpha. And the second one, y of t equals b, a different amplitude, times sine of omega t plus a phase that I'll call beta. Now, I want to know what the sum of these two waveforms is. X of t plus y of t. The easiest way to do this is to use complex numbers. But until you've learned about complex numbers, the way to do it is to assume that the answer is a sine wave. It's just a sine wave of an amplitude that we don't know yet, c, and a phase that we don't know yet, which I'll call gamma. So, this plus this equals this. Now, if I use the useful trigonometrical identity that sine a plus b is sine of a times cosine b plus sine of b times cosine a, then I could express this as a sine omega t cosine alpha plus a cosine omega t sine alpha. And I can express this term y of t as b sine omega t cosine beta plus b cosine omega t sine beta. And those two added up have to be equal to c sine omega t cosine gamma plus c cosine omega t sine gamma. Right, this has to be true at all possible times, including time t equals 0. And at time t equals 0, sine of omega t would just be the sine of 0, which is 0. So that term and that term and that term would disappear. We could divide through the remainder of the terms by cosine of omega t, because they all have the common factor of cosine omega t in them, and that would just leave us with a sine alpha plus b sine beta equals c sine gamma. Now we could also consider the time when omega t is pi over 2, or 90 degrees. And at that time, the sine of omega t will be 1, and the cosine of omega t will be 0. So all of the cosine terms would vanish, and the remaining terms would give me that a cosine alpha plus b cosine beta equals c cosine gamma. Now if I want to know what c is, I can proceed by squaring both of these equations. And adding them up. And that would give me on this side c squared times sine squared gamma plus cosine squared gamma. Now, sine squared gamma plus cosine squared gamma is 1. So that's just equal to c squared. So I can work out the amplitude of the sum of these two. It's the square root of A sine alpha plus B sine beta all squared plus A cosine alpha plus B cosine beta all squared. Not a particularly easy to remember formula, but that is the result that you get. As I say, don't worry too much. There is a much easier way to do this coming up after you've learnt about complex numbers. If you wanted to work out the phase, gamma, then you would do it by taking these two formulas here and dividing them. The c's would cancel out. We would end up with tan gamma equaling A sine alpha plus B sine beta over A cosine alpha plus B cosine beta. And once we've got the tangent of gamma, getting gamma itself is just taking the inverse tangent of this. Again, not a particularly neat equation, and one that I don't plan to use because I'm going to wait until you've learnt about complex numbers and then we can all do it the easy way. Okay, and that's the end of this one.